Okay, so more of 9.5, and this is number 25, and this is our series, and it looks like it's an alternating series, doesn't it? Negative 1 n plus 1 over 1 n times the natural log of n. So first of all, test for absolute convergence, because if it's absolute, then we're home free. So let's take a look at this. So this would be the absolute value of this series, and that would get rid of the negative 1 part, so I just have the summation n equals 2 to infinity of 1 over n, natural log of n. So what I'm going to do is I'm going to use the integral test on this. This is f of x, and this is continuous, positive, and it is decreasing for x greater than or equal to 2. In other words, as this gets bigger, it gets smaller overall, because the denominator keeps getting larger and larger, so the fraction gets smaller, smaller, smaller. So I'll try the integral test. I know it will behave the same way as this integral, or this integral here. This series, written as this function, will behave the same as this integral. So 2 to infinity of 1 over x, natural log of x dx, since that's going to be the limit as b approaches infinity, of 2 to b, and then that's 1 over the natural log of x times 1 over x dx, and this looks like this is 1 over u du. What's the derivative of the natural log of x? 1 over x. So the antiderivative of that will be just the natural log of this. So the natural log of the absolute value of the natural log of x, okay, because this is a 1 over u du, this is a u, so it's the natural log of u, okay. And then we can evaluate this limit as b approaches infinity, so I can write this out, and this is going to be the natural log of the natural log of b minus the natural log of the natural log of 2. And as b goes to infinity, this term is going to go to infinity, because this would be huge, and this would get even huger, so, because they're both increasing functions, so therefore it's equal to infinity. So it does not converge absolutely. Sorry about that. Okay, so it does not converge absolutely. So now we have to test for actual convergence and see if we've got conditional convergence. So I'll take a look at this, and again, this is a alternating series. Okay, so look at that. I hope that makes sense. I should write it down there just to okay. Now you might say, well, what if we did this first? If you did this first and then converge, you don't still have to test for absolute convergence because you want to check for conditional convergence. So you're going to have to do that anyway. So, but if this works out and it converges, then you're done. So that's why I think it's easier to try this first and then this. Okay, so we'll check for convergence and see if it does converge conditionally. We know it doesn't converge absolutely. Okay. So this is an alternating series, so this is my u sub n for n greater than 2. Is it positive? Yes, it's positive. Is it decreasing? Yes, it's decreasing. And if I take the limit as n approaches infinity of this, does that equal 0? Yes. So it meets all three criteria for a converging alternating series, so we can say that this series converges by the alternating series test, sometimes known as the Leibniz test. Okay. So it does converge. So the series converges conditionally. That means it converges, but not absolutely, just regular convergence, not absolute convergence, so therefore it's conditional convergence. And then you want to try the error bound. Well, I'm just going to, for the 99th term, so I'm going to put 100 in. So I get the error bound for n equal 99 is 1 over 100 times the natural log of 100. 1 over n, that would be 100 times the natural log of 100. And I get 0.00217. Okay, and let's take a look at number 26. And here's 26, and again, this is my series. It's an alternating series, but first of all, I'm going to check for absolute convergence because I may get away with it, so I won't have to do the, it may converge absolutely. So let's take a look at this. So if we take a look at the absolute value of this, we get n squared over 2/3 n. So let's try the ratio test on this one. Doesn't look like any of the other tests would be applicable. So a sub n plus 1 over n, we would take the limit of that. That's going to give us an L. And if it's less than 1, it converges. If it's greater than 1, it diverges. And if it's equal to 1, well, we've got to try something else. Okay? So this would be the nth plus first term. So this would be, and this is absolute, so we don't have to worry about the negative 1 to the nth. So it's n plus 1 squared, 2/3 of the n plus 1, then times the reciprocal of this, which would be 1 over n squared. And then times, and if I take the reciprocal of this, this would be 3/2 to the n. If you put it over 1 and flip it, it ends up being this. Okay, so this is going to be, again, this is the limit as n approaches infinity. So this is going to be n squared, and this is going to be 2/3 to the n times 2/3. I'm going to break this up to the n and to the 1. And then over here, I brought the n squared over here, so I have n squared, n plus 1 squared over n squared. Okay? And then this is 2/3 to the n, 1/2, and then this. So I kind of rewrote it like again, did a little bit more rewriting, and I've got n plus 1 squared over n squared originally, and I got the 2/3, and then I could put both these under the n power. So 2/3 times 3/2 under the n power, that just is going to be 1. And then I multiplied this out, so it'll be a little bit easier for some of you to see. N squared plus 2, n plus 1 over n squared, times my 2/3 times 1 to the n, which is just 1. And the limit of this, well, we can see that the highest degree terms in the numerator and the denominator are both second power. So we just look at the ratio of the coefficients, which is 1. This is 1, so that's my limit, 2/3. 2/3 equals L. Since 2/3 is less than 1, L is less than 1. So therefore the series converges absolutely. So I don't have to worry about conditional convergence. See, I'm done. That's why it's nice to try absolute convergence first. If you tried the other, because we know it would converge. If it converges absolutely, it converges. So if we tried it just looking at the series, then we know that that series converges. But then we'd have to go back to check to see, if it converges absolutely, to see if it's conditional or absolute convergence. So there we go. All right, and we want to try the error bound for n equals 99. So that's just going to be 100 squared plus 2/3 to the 100, and that ends up being 2.4597. I think it round off to 2.46 times 10 to the negative 14. So when you work that out, that's what you should get. Okay, so that's number 26. So there's a bit to these problems. Try to get as much out of them as you can, and you'll be in pretty good shape.